So now it's streaming. So you can test if it's working. So I can start recording as well. So the projector is on.
I believe it's too dark, like for the green screen.
Switch it off. Light.
So 5 seconds as usual. Can you stand where you want to stand in order to adjust the
Yeah, I
camera?
guess somewhere here. And I can
Okay.
reach for the laptop. Is he online?
Can you stand where you want? More like you know that.
That is okay. No, it's okay. So can you go to the left a little
Okay.
bit? Left.
Like you know that.
Don't do it.
10 seconds. 15 minutes.
Yeah, that's you.
Yeah. So everything is fine.
Everything is fine? Yeah, I think I'm ready. So when you're ready, I'm ready.
And how will you speak? You have a headphone?
No, I think that this microphone is good enough.
By the way, how long do you think it will take? Because I have another lecture to attend, my own, another course.
1 hour, maybe 15 minutes.
Okay.
Max.
So
145.
I can try to be relatively quick.
no, like it depends on you. Whenever you go, I'll be
He
here.
will just come back to collect all of
Yeah.
this.
I should leave my phone somewhere close so I could see the timing is.
No, like it depends on you.
More or less what time it is.
I think you can get started. It's not really hard.
Yeah.
We take a leave, Radham, and all the best.
Okay, thanks.
Okay. So see.
So hello everyone, and today I will present the introduction to biomechanics or modeling of human musculoskeletal system. And this lecture, in contrast to Aki's lecture, will have a little bit less equations and more pictures, though I haven't seen the latest Aki's lecture, so probably I'm not that far off from this standard. My name is Adam Kladowski, and I work together with Aki in the Laboratory of Machine Design. And well, this should bring you some kind of interest to biomechanics and other applications of multi-body simulations than simulated machines. So let's start with the motivation. Why do we even care about biomechanics? And one of the reasons is to increase our well-being. So prosthesis design and optimization. Of course, if you have a pain in your knee or some other joint and it is heavily damaged and it requires some replacement, then you need a surgery. And the surgery usually means replacing some of the biological structure with a man-made components. In this case, for example, there's a damaged cartilage, which in the human body acts as a bearing surface, so it has to be smooth and without any deterioration so that it could work. If it's replaced with some kind of titanium implant or some other metal that is approved for medical purposes, you would like it to perform exactly the same motion, and you would like it to transfer the loads in exactly the same way. And because the material is completely different, it's much stiffer, it will behave differently. So of course the patients will feel the difference. And every knee is different. There's no one size fit all there. Like even with the shoes, you have different sizes. With the implants, you have also different sizes, but they have to be adjusted for a specific geometry. And to do that, you actually need to have some sort of a simulation. And geometrical adjustment is one thing, and that can be done based on medical images and then the CAD design. But then the other thing is how this compound actually transmits the load from one bone to another, what are the friction properties, whether this will be compatible and provide comfort for the end user. And those things to evaluate, either you can make lots of surgeries trying by trial and error, and nobody wants to do that, or you can evaluate that kind of prosthesis first in a simulation environment and test and optimize it until you're satisfied, and then you have a high chances that after one surgery it will be a solved case. Now, another implant is a hip implant. So that's a typical and very painful thing if you have a broken hip bone. And then if you need this kind of an implant, it's basically the part of it is a nail which goes inside the bone, and it's fixed there with some specific cement. And then there is a mechanical ball joint component which is outside. And again, they are on different sizes, and because our bones are responding to loading, so if the loading is low, bone is starting to disappear because by the default it's optimizing for the light weight of a body structure. If we are using our bones heavily, then of course the bones are growing. And the same thing goes with the implant. So if the implant takes too much load on itself and doesn't transmit enough load to the side, to the bone, then what happens is that the bone starts disappearing around it and the implant gets loose. And that requires additional surgery. So to make this kind of implant compatible with a bone, you also have to optimize it heavily for a specific use case, and optimizing even a family of those devices requires a lot of computation and a lot of studies from the mechanical engineering department. Now, another type of biomechanical application, again, as a resource to help humans, are some sort of a mechanical prosthesis which are used as a replacement, for example, here for the foot. So you can have a wooden leg or some kind of composite leg, and it will be just a stiff component, which gives you very hard kind of a replacement, but it's probably cheap. Or you can have something which is mechanical structure, and in this case, you can basically store the energy from walking whenever you have a heel strike, and then restore part of that energy using relaxing the spring during the push-off phase. That's what normally your foot is doing. This device is just mimicking it. And of course, to get a response of this device, you cannot just come up with the design out of your head and say that, okay, this spring will have that stiffness, this damper will have that kind of damping coefficient, and it's ready. You need to actually test it, optimize it, figure out what are the parameters for different size of people. And then when you have a specific subject, you should still fine-tune those parameters to give the best performance. Now, another optimization that happens in biomechanical studies is, for example, in sport engineering. This is some really old study which shows the air drag. If you remember the ski jumps from, let's say, 80s, the style of jumping was completely different than it's used nowadays. And it wouldn't be possible to figure out the better styles for jumping without simulation, or brave people trying to break their neck, trying different styles before they really realize that it's working or it's not working. So this type of studies, which includes fluid dynamics and multi-body dynamics together, are also part of biomechanical studies, and they can be quite helpful in designing new sports equipment, as well as improving the existing sports equipment to get better performance. Now, whenever we're thinking about sports, we also go to the gym exercises, and there are some innovative devices that come to the market once in a while, and those devices have to be based on certain human kinematics. So if you try to reinvent the bicycle creating something like this, I think it was called Orbitrack, you need to have a certain range of motion, both for the upper body and for the lower body. And this range of motion should be based on human dimensions and capabilities. So to optimize design of such a exercising equipment, what you need to do, you have to, again, put a human model together with the model of the, let's say, the conceptual model of your device, then use a parametric analysis, changing different lengths of the links, radiuses of the circle where it rotates, and until you get the range of motion which is actually beneficial from the exercising perspective. And of course, with that kind of device and a human model on it, you could actually evaluate what is the influence of the exercise on different muscles, what is the loading in the joints, something that you cannot see directly from measurements. If you think about rowing, of course you want to practice rowing not only on the lake, so then you need some sort of a resistance, and coming up with a design which is relatively simple, but at the same time mimics the rowing motion quite well, and the variable resistance which is changed when you change the velocity. It isn't straightforward, so of course to get to that design you have to do a lot of tests and a lot of simulations to get it right. And what you can of course optimize, you can see the dimensions of the device, you can optimize what is the resistance that should be created, how the resistance should change with the increase of the force, or when you try to increase the speed. So if you correlate the data measured from the lake, then you can get some kind of a curves that gives you the input for the design, but you have to still check the mechanical design with the human, whether they are compatible to convince potential buyers. Then of course there's a fun department, so you can have those kind of spring legs attached to your shoes, and that will allow you to jump quite high, so you could reach maybe 3 meters of jump. And of course we are not designed to jump that high by nature, so the device have to take the shock whenever landing. So the design have to be made in a way that you are able to jump high, but you can also land safely, not overloading your bones, because even in normal running you can reach the loading on your joints, which is 10 times your body weight. So imagine jumping, you want to limit the peak values of the jump force and then smoothen it so that it is within the safe region, so that it's not causing any permanent damage. Then automotive industry have been using biomechanics for quite a while. It all started with the crash test dummies. So of course the crash test is expensive when you have to crash the fully featured car, and one crash test just gives you a small dose of information, so you have to crash a lot of vehicles to get a decent set of information, and nobody wants to build a car, crash it, and then realize that they have to redesign it completely and crash another one, because that would be an endless loop, and it would take years to get one good design. So instead what is happening, the virtual dummies are first placed in the car models in a FEA system, where you can have the deformable bodies. Also a combination of FEA and multi-body dynamics is quite often used. And then you can see how different components in your car respond. And in addition, you can also simulate, for example, the hardware that is controlling the whole process. So when your airbag opens, it's very important when it opens. And the timing is in a millisecond range. So it cannot be too late, because then you're already having enough velocity to hit the steering wheel, and a blow in the face is actually making things worse. If it's too early, then before you actually hit, it doesn't have enough air to cushion the impact. So it has to be timed exactly, and to study when to trigger the device, how the explosion happens, so that it feels the airbag close enough. It takes a lot of testing. The first Mercedes which was tested with airbags, which was shown publicly as a research part then, after the airbags opened, actually the sunroof was blown up from the car because of the increase of the car pressure. So these are the things that you probably won't think about while designing, but they come up in tests, and if you use the simulation at that stage, then you can find the mitigation for side effects that are difficult to predict. Then on the right bottom corner, there's an example from the race car. You can notice that, for example, Formula 1 cars have been redesigned quite heavily to withstand high impacts, and, for example, make sure that parts that are falling off from the car during an accident are not harming the driver. That's one thing. And second thing is having enough energy-consuming elements that will slow you down, preventing you from damage. So the cage around the driver has to be stiff, but at the same time there has to be a cushioning elements which take the energy dissipated so that you can actually survive certain crashes. And judging by the amount of crashes and fatalities in different motorsports over the years, it has been improved quite significantly thanks to the simulation. Now, after that long introduction, we can get to the core of what the biomechanics really is. And it's simply application of mechanical principles to biological structures. And we can study humans, we can study animals, we can study plants, individual organs, cells, whatever biological structure we can think of. Now, what you have learned so far is how to deal with a man-made structure. And a man-made structure, like for example, excavator or a mobile machine, this is what is quite often studied because building prototypes for those devices is really expensive because there's lots of steel, lots of elements involved. And figuring out good control system for those is also not trivial because you would like to first study how the user can use it and how it feels, and then decide about certain parameters which affect the responsiveness of the device. And each such device have three major components. So there's a load-bearing structure, so all the metal parts that carry the load. There are actuators to make things move. And of course, so the movement makes any sense, you have a control system, which in machines is always some kind of electronic subsystem. Now, if you compare it to a human body, we can also find similar structures. So as a load-bearing structures, instead of metal, we have bones, and they create the whole skeleton that holds us together. Then we have muscles as actuators, which pull the bones to create different motion patterns. And then we have a brain and central nervous system as a control thing and sensing at the same time. So sensing was not mentioned in both pictures, but it's kind of implied that the sensing appears somewhere. So we can feel what's happening with the body. Now, if we think about those two systems from the perspective of a modeling, we don't see excavator, we don't see human, we see just a bunch of flying potatoes connected with joints, forces attached between them, some springs, dampers, and this is what we are actually dealing with when we talk about multi-body. And once we see this visualization of the pretty picture where we decide which components are moving, how they are connected, where forces are applied, we can actually go down to the equations, and forming the equation basically links, mass, acceleration, forces, and all the other influences that we want to count in the model. But basically, we're always talking about forces, accelerations, and different inertial properties which affect this behavior. And it doesn't really matter from the mathematical perspective if we're talking about the excavator, space shuttle, human, or a lizard. It's always modeled similar way. What is different is basically the control algorithm that we use. And what is different is the real counterpart that we are trying to model. So the phenomenological models for individual components, how the forces are developed, how the damping is calculated, they are different depending on the model. The geometrical structure and inertia is of course different, but the mathematical model behind is basically the same. So we can reuse the knowledge that we have for studying something different than machines. Now what makes things a little bit different is how we model the joints. So in the man-made structures, we usually use a sliding joint, rotational joint, and then sometimes a ball joint. And these are the most common joints almost everywhere. So if you have a rotational joint, just put bearings on it, and then it rotates. If you have a sliding joint, there are several options to do the sliding. Either you grease the two parts and they slide with respect to each other, or you put some rollers to make the sliding easier. There are a bunch of ways, and each of them will work quite well. But now when it comes to a human body, well, if we look at the knee, the first analogy we can think of is a hinge joint. And that's a very good analogy for small range of motion. So when you're walking, running, you can assume that it's a hinge, and that's pretty well justified assumption. But if you want to be a little bit more detailed, you realize that it's actually closer to a spherical joint, but with some added degrees of freedom. So it can not only rotate in all three directions, but it can separate partially. It can be pressed together a little bit, deforming the cartilage. And it can also shift in different directions. So it allows basically all the degrees of freedom, but in a very constrained way. And the way how it's constrained is by the geometry of the two contracting surfaces. So if you look at the cartilages which touch each other, then that will constrain our motion. So if we replicate that, we can actually get some kind of a pattern how the knee can move and see how the rotation axis is slowly moving when you have a deep flexion of the knee compared to fully extended knee. But then to keep the leg together so that it wouldn't fall apart, we need to have some springs in a model, and in reality these are ligaments. So there are crucial ligaments in the middle, lateral and medial, so on the outside and inside of the leg, ligaments that keep the leg together. So whenever you're lifting your leg, it's not being held just by the skin outside and muscle, but the ligaments actually keep it together, so that there is some kind of pretension between the surfaces, so they are always in contact, so the leg wouldn't rotate or jump out of the joint. And basically that's why when there is a failure in those ligaments, you get a lot of pain because the knee starts working in a completely different manner than it should. And of course, when you're modeling, you have to make a decision at some point, how accurate you need to be to get your results. So you have to set your point in the model to something achievable. So if you want to model the whole body, you generally want to simplify the joint as much as possible. And if the joint angles are within certain limits, you can have a decent result from that. But if you have a deep flexion, if you have just a model of a fragment of the body, then you can go to more details and try to get more and more into how this joint really should be modeled and how much accuracy you can put there. Similarly, like in case of an excavator, you can have a very simple hydraulic model for the cylinder producing the force, or you can have a model which models all the hoses and elements on the way, which affects the elasticity. So let's go forward. Now, what kind of methods we have in the biomechanics? So of course we have two sets of methods like everywhere. We have experimental methods and computational methods. When it comes to experimental methods, we can analyze motion. So basically do a series of tests. For example, take pictures, which was one of the first types of motion analysis in biomechanics, basically taking pictures and analyzing step-by-step movement of a sportsman or a horse, for example, and seeing how it performs and figuring out some ground truth of what happens by solving, for example, a set of static cases for individual frames and trying to assume what is happening there. We can measure some of the external forces. So for example, if you punch an object or if you lift an object, you can have sensors that measure actually this activity. If you're walking, you can have sensors in your shoe insoles, or you can have sensors on the floor and measure the reaction forces. And that gives you a lot of information of what you're producing. For example, measuring ground reaction forces while running or walking gives you the information, what are the forces really that pass through your body. So if your body center of mass is somewhere around your pelvis, you can assume that the forces that you're reading under the feet correspond to more or less everything that goes through your leg. So these are the forces that your legs have to deal with, and of course all the joints on the way. So pelvic joint, knee joint, and ankle joint. You can measure muscle activation using EMG. So these are the surface electrodes that you can add on the skin, and then you measure the signals that are going to the muscles. And that's something interesting because those signals are not linear, as in case of signals going, for example, for machine control system opening the valves. So in a proportional valve, the signal is proportional to the flow. But in a human mechanics or animal mechanics, if you measure EMG from the muscle, the signal is correlated to the force, but it's not a linear relation in the whole range. It can be linearized in certain cases, but it's not linear per se. You can measure maximum energy, oxygen consumption, for example, using an oxygen mask, and you can basically measure how a person is breathing. You can measure lung capacity. There's a bunch of things that you can actually measure. The benefit with the measurement studies is that usually what you're measuring is the data that you're expecting to get. So the interpretation of the result is quite simple. So if you measure the force, you have the force. Those methods are quite reliable. you can have a lot of visual inspection options to check if the sensors are in the right position, if everything is working. You can perform tests with some kind of dummy samples to test if the response is corresponding to what you need. But the limitations are usually the measurement conditions. Not everything can be measured. Sometimes the measurement have to be done, for example, indoor. So how do you measure, for example, a skier outdoor if, let's say, your equipment requires to be indoor in a warm condition and it has to be stationary? Well, it means that this kind of equipment is not applicable to a skier. If you develop equipment that works for a skier outdoors, there might be some limitations on accuracy, or there might be some other inaccuracies related to the forced minimization of the system. The number of parameters you can measure is quite limited, because even if you try to apply sensors on the human body, there's a finite surface that you can measure, and basically you can measure things which are outside. It's difficult to measure what is inside, especially if you're on the move. So if you would like to see the inside, you can put a person to a CT scanner or MRI device and see what is inside. But at that time, the person cannot move. If you want the person to be moving, then you don't know what's happening inside. So you cannot see, for example, how organs are moving during a jump or something. If you would like to evaluate the risks for an injury, that's something you cannot do with the experiment easily. And preparing an experiment, executing an experiment, this is something that takes a lot of planning. It takes a lot of people involved, and it takes a lot of resources to actually get it done. And it's not always easy. Now, when it comes to computational methods, maybe let's start from the benefits, is you don't have really a limit of parameters that you can estimate. You can estimate as many parameters as your computational power allows you. Having access to supercomputers means that you can measure a lot. You can measure really detailed parameters at any location that you really want. You can measure internal parameters which normally in physical world are not accessible. So if I want to know the force in my knee, I can measure, for example, ground reaction force, I can measure acceleration of the body and then calculate it. That's one way. But I could also run a simulation where I have specific motion and I actually calculate the ground reaction force, I calculate all the other forces, and then I can have a detailed distribution of forces within a knee. And if my model is valid, then of course I have a good result. And of course computational models are not invasive. So with good computing power I can study hundreds of people in different conditions. I can study dangerous situations without harming anyone. So for example, what kind of forces are experienced by a base jumper when he's landing? Well, not many of them would go with, let's say, additional equipment on them just to have some sensing. But if I just simulate the same thing, I can get the results without anyone risking anything. Now, about the limitations. Building person-specific model is really time-consuming. Because first of all, you have to measure the human, then you have to build the model. And if you think about the geometries of bones, geometries of human muscles and stuff, these are not simple engineering shapes. This is not just a rectangle or a cylinder or something else. It's always some kind of a complex, funky shape. And to make it even more complicated during operation, for example, muscles change their shape. So that's how everything works. So that adds complexity to build the model. Because we can measure things that we cannot measure in physical world, it's sometimes difficult to verify the model. You can always validate against certain data sets. So if you have some kind of idea of what to expect within the parameters that you can measure, then you can use those known results as a base point to validate your model, and then use the new data as something that, okay, this is my new knowledge that I generated. I cannot validate it, but I present it, and then people can dispute making different models to validate my results. Now, when it comes to methods that are available from computational standpoint of view, we have, of course, static analysis for simple cases. Kinematic analysis, when we want to see just the range of motion, for example, like if we have a golf swing, we could look at the range of motion. We could also go further and try to look at the forces or the formations. And in that case, again, we have some tools that help us to do certain things. So if we look at a single component, and we would like to know what are the forces within it, what are the strains and stresses, we can use finite element model. apply forces that we have to know from somewhere, and then we can see what happens inside the component. If we want to study something moving in a long time, then most likely we would like to know what are the interactions between moving bodies. So for example, joint forces, and this is where the multi-body dynamics comes in handy. And having the results from multi-body dynamics, we can of course feed them to finite element model to see what happens inside the bones or the muscles. And that's basically a role of flexible multi-body dynamics when we have a combination of multi-body code and some sort of interpretation of the elastic property. So either embedding finite element model fully, or using component mode synthesis, or using some other approximation that allows us to see actually the deformation. Now, when it comes to experimental methods, just to show you more or less how things are working. So on the top, we have, for example, a sensor that can be installed between the prosthesis joint of the knee, and that sensor can be later on powered wirelessly through induction to gather the data about the load in the knee joint. And such study has been done, and it brings, of course, the information what kind of forces can be expected in the knee. But because the whole knee is artificial, what we know from that study is what are the forces in artificial knee. Now, if we have a real knee, which have similar geometry, but it's slightly different. People change their walking style after the surgery. So, of course, the forces will be different. But we are already in the ballpark of the result that we can expect. So that's why it's quite interesting. But, of course, somebody who will get this kind of prosthesis installed as a part of experiment, he will live with that prosthesis for as long as possible. So this prosthesis stays. So this instrumentation is kind of staying inside the patient. And as long as he's willing to cooperate, of course, you can get some additional data from different physical activities. So this is useful, but difficult to organize practically. On the right-hand side, you have a sensor which are strain gauges installed on the surface of a cadaveric bone. So a bone taken from a dead body, basically. And then if you have that kind of bone, you can put it to a robot arm and make the robot arm make the motion so that two bones can touch each other, applying the forces that we have measured somehow from the other studies, and then see what really happens. But of course, then when we're dealing with a dead bone, its response is different than a living bone. However you would preserve it, it's not that easy. And as you can see on every condyle of the cartilage, you can have just 1, 2, 3 strain gauges to measure some stresses. You cannot actually evaluate the stresses over a big area. That would be quite difficult to realize practically. Then on the bottom in the middle, there's another cadaveric bone specimen where there are some strain gauges attached. And you can see that there's just like, I don't know, 6, 7 strain gauges attached everywhere. And basically, for those strain gauges to operate, you have to have wires going to them. And that wire starts to contribute the weight of the bone at some certain point when you start adding. So the response, of course, it starts to deviate. So you have a kind of a limit of how many sensors you can really put. And again, this kind of a bone can be put to a testing device or a robot that will move it around, press it from different conditions, and then you can see how different loading affects the bone, and from that you can derive the bone models. Having good bone models, you can apply them in the simulation, and then in the simulation you will learn what happens inside. So something that you cannot measure from that kind of thing. And another sensor which is visible here on the left is basically an implant for the hip joint, which also has an induction coil for providing electricity to it from outside, and then it has sensors for forces in the hip joint, and something like that has been also done. So this is from some other studies. So we have some measurements from a real human, but again from industrial-made joint and not a natural joint. But of course we have to assume that the general forces should be similar. Of course the damping coefficients and everything else is affecting the peaks, but we should have the ballpark of the values that we can expect in that kind of a joint. This is another set of experimental methods. This is from Revascula, and this was done for motion capture that was at that time recorded using normal cameras. So the cameras basically saw the daylight, and you can have a visual image. So to see something, there was a black background. The guy was dressed black, so that he's basically invisible. and the only visible elements should be those reflective balls. So there was a lot of light around, and that light made the balls reflect. On the surface, this green carpet, basically underneath there was a large force plate. So when the person is walking over, I think it was like 10 meters, over that long range, so he can make a few steps, and we can get the ground reaction force, 3 components of the ground reaction force, to see how he's actually how he's walking and how the ground reaction is distributed. Now, to make that thing work, which is on the left, we needed the equipment which is on the right. So you can see that basically there's a lot of wires and a lot of machines, and you need some power for that to keep it. So except studying this walking, running, jumping in a short 10-meter long span, which was then at that time, it was something really extraordinary to have that long force plates. To study that, you need a lot of equipment, and you're constrained to one environment where you can do it. So if you would like to study how the guy is running, for example, during a marathon or something else, impossible with that devices, you would have to have an instrumented road, which would probably cost a fortune and not easy to realize in practice. Now, another type of measuring device. Here we have an ultrasound head on the Achilles tendon. So from the ultrasound, we could see basically what's happening with the fibers of the muscle and the tendon. Then there are some EMG sensing elements on the leg to see actually what signals the muscles are producing. And the guy is on a platform that can slide, so when he's pushing his weight up plus some extra weight, we can see what actually happens in the muscle and what is the muscle activation. Then to measure what is kind of a torque that the ankle joint can produce, and from that derive the parameters, for example, for the muscle, there was another device that was shown here, and then there was basically a torque sensor. So this is like a big gas pedal, and you're trying to press it with the leg, and then we can measure basically how far you can press it. And that's also one option. And again, here there was also ultrasound head on the Achilles tendon to measure the formation there and show what's happening internally. So again, one place that you can measure a few sensors and a big set of equipment to get some results there. This is from a walking trial. This was used already with the infrared camera, so there's no need for a specific background. And when the subject is walking over force platforms, there's actually a force platform underneath, and there are 2 force platforms here that are more accurate. They give 6 components of the force, so 3 forces and 3 torques. So when the subject is actually stepping on those force platforms, we get from 2 steps more accurate data, but on the whole length we have the long force plates that measured the ground reactional force for the whole thing. And then there were 2 photocells marking the starting and ending point to start and synchronize the recording from different cameras. And that's how it looks from the outside. So basically there was lighting, background, some amount of cameras, front, back. In this setup there were 4 cameras. Later on, setup with more cameras is used because the more cameras you have, the least likely it is that the markers disappear from cameras. And to have a 3D position of a marker, you have to see it at least on 2 cameras which are under some angle with respect to each other. So then you can have all the 3 locations. If the marker disappears from a few cameras and is visible only on 1 camera, then you have kind of a planar view. So you see 2 coordinates with respect to the camera system, but you don't know the depth. And that's something that you can reconstruct later on manually with some curves, but it's not that accurate result. So then for the motion capture, you have to use some markers to see how the body is moving. And the point is that on every moving part, you need to know the orientation of that part, and you need to know the position in 3D. And of course, if you have a single element flying in the air, you need 3 points basically to set the rotation and orientation, because 3 points define a plane uniquely in a 3D space. So you know how the plane is oriented and you know where it is located. Now, because the knowledge about the human body, we know that there are joints, so if I move the hand, at the same time, there are certain relations between body parts. I don't need 3 markers on every body segment. So I can have less markers because the motions of individual body segments are related. If I have hand like that, I have to have the forearm and the arm located at a certain angle because they have to meet in a certain position. And that's how the protocol has been designed for locating the markers. They have the names which come from the name, like for example, tib from tibial joint and so on. And basically from the perspective of measurement, you try to have as little markers as possible, because if you have a lot of them, then it's easy that during the motion they get confused. So when you pass, for example, two hands next to each other, then you might actually lose track of which marker is on which hand, and you start tracking them inversely, and then you get something crazy, like your hands are swapped at some point. So to avoid that, either you have to use an algorithm, or you have to manually check the reconstructed data and make some manual fixes that if the markers are not assigned properly. So how the motion capture works, we have n cameras, the more the better. Then for those cameras, you have to have a calibration. So when you have a camera, what you see from the camera is a pixel, and you can know where the pixel is within the camera space. So if it's like 10th pixel from the left and 5th from the top or somewhere else. But how does this correspond to the 3D location? It depends on the data from multiple cameras. So if you see the same object in a 3D space from at least two cameras, then you can attribute it to two different planes where you project it. And from those two projections, you can actually reconstruct the 3D location. But you have to know where the cameras are located, what are their optics, so what is the focal length of the camera, and either you can measure those values and somehow put in the model, or you can, which is less error prone, basically bring objects of known sizes in the 3D space, put them in different positions, and then record what you see on the cameras, and from that reconstruct the matrix for transformation. And currently this is done automatically. It used to be done manually. Today you just have to walk around with a magic wand, moving around the space. Then the system records the image of the magic wand. It knows the dimensions of the actual object, so it can find it in the 3D space and in the camera space, and then find the corresponding transformations. And then once you have that, this is a fully automatic, and it's been fully automatic for quite a while. So you can trace every marker how it's moving on the way. So first you stand in some kind of known pose, usually it's a T pose. Then the body is recognized and the markers are known where they are. So they are found and they are labeled in the system. So then the computer software knows where are the physical markers. And from that moment, when you start moving with at least 50 frames per second or 100 or 1,000, even better, you track the motion of individual markers. And because the small time step between the frames allows you to see how far they are moving, you just try to find the closest one, and you assume that there are no swaps between them. And then you do the transformation of the image to 3D, and you record the trajectory. So the amount of data that you record later on is quite small, because if you think about the images, 100 images per second, with good resolution, this is quite a lot of data. But if you process it on the fly, extracting just the markers positions and removing everything else, then you have just, 20 markers or 27 markers and that many data points per each time step. So that is very small amount of data to process later on. Now, what we can compute from the models is, for example, muscle activation patterns. We can compute muscle forces. We can compute contact forces, joint loading, bone loading, strains and stresses within the bone. And also we can compute, for example, fracture healing process. These are just some examples how the biomechanics can be used in practice. How we build the model for the biomechanics. So first we start with the body parameters. There's good amount of research on how to generate like generic human based on just few parameters. So knowing height, weight, gender, ethnicity, and age, and sometimes BMI or something else, will allow you to get a decent looking human body representation. So you'll get the bones, which have reasonable inertia properties. You will have muscles, which have some parameters that describe what is the force of the muscles and what is their speed. And then you can fine tune it and use it in a simulation. So that's what you're getting. Then on top of that, you add the muscles. The simplest way you can add muscles are just straight line of actions. Of course, this doesn't work when you have a big joint motion, because if you bend the joint like this, then the muscle can actually pass through the joint, and then from the muscle that would extend the joint, actually it causes to be a muscle that would compress the joint. So that's something that you have to deal with, having, for example, a wrapping of the muscles around the joints to represent reality. So that makes a more complication, but that's something you can do. When you build this model, you have to consider a few things, like you have a model, so how many details you need? Do you need really the whole body, or do you want to study only the hand? Do you want to have very precise muscle models, or can you live with something simpler? How do you model the muscle geometry? How do you model the joints, how complex you are? This all affects computational load and later on how fast the model could respond to certain things. And of course, where do you put elastic elements that you are interested in strains? If you're interested in strains, for example, in the chest, you would not have to put elastic elements in the legs, which you don't model, unless you think that there's some effect that will contribute to what you're calculating, and then you put the extra load there. Then building of the human model basically starts from anthropometric measurements. You can prepare the flexible models separately, and then you join it to have a skeletal model. Then to that skeletal model, you still need joints. So you define the joints mathematics. You have the muscle models, contact models, so all the forces that come from outside, and external forces which can affect. So for example, gravity, or if you're pressed by something, then this is also included. How to get the bone geometry? So one of the things, if you have a cadaveric specimen, you can basically take the bone, do a laser scan of that, and then reconstruct it, take a bunch of pictures. There's lots of options to do it. But if the bone is inside a living human and you don't want to kill him for the experiment, or wait until he dies, then you have a computed tomography or magnetic resonance. And these are the most used applications. And the key difference between them is the principle of operation. They look kind of same, but internally they are totally different. With the computed tomography, the X-rays are used, and that makes it quick. Because the X-rays go quickly, there are detectors, and you get very accurate images in short time. So for example, having the images of the lower leg would take, I think, 2 minutes or something like this. Now, if you go to magnetic resonance, you don't have the radiation, which is kind of cool. But it's like a giant inefficient microwave oven, which basically studies the response of the water particles in your body. But it's slow, so the same lower leg would take 40 minutes. So if you want to get a decent image of the lower leg with lots of slices, you have to not move for 40 minutes while it's scanning. So you have to kind of support the patient to get it done. So it's more difficult to get it. The other benefit of computed tomography is that the attenuation of the radiation is proportional to the density. So every voxel value, so this 3D pixel, tells you how dense is the matter underneath. So you can recognize the bone from, for example, water or fat or some other things. From magnetic resonance, it's not the thing. It's more like the water response. So you cannot really tell the density. So from magnetic resonance, you cannot reconstruct reliably the density of the bone, but from the computed tomography, you can. So after what you get out of this machine is basically a set of slices. And each slice is like an X-ray picture of a thin section of a body. So not the X-ray that accumulates everything through the thickness, but just a thin slice. So from those slices, you basically have to find the contours of the elements that you want to segment, usually bones or muscles. So you just have to get the contour of every element, and you can get this segmentation automatic to a certain extent, but closer to the end of the bones, basically the image which shows the bone and which shows the tissue around it kind of has the same color. So it's difficult to say where is the bone and where is something else, and algorithms are also having problems with that. So that might be some manual work to do. So once you get those contours, you can of course fit a 3D surface over it, and the 3D surface is your model. Now once you have a 3D surface, it's a basically solid model. You can make a surface model, mesh, but solid is more appropriate for bones. So you just put mesh there, and this is an example with tetrahedral elements. They kind of scale nicely for kind of weird geometry. And this is with 5mm tetrahedrals, which gave you like 21,000 of elements. But what is important is like 4,700 nodes, which is a decent number to calculate in finite element software. Now, if you want to be more specific, this is more advanced bone model that we made. This had 65,000 nodes. So in this case, we were mostly concentrated on the neck. So there we had a really fine mesh to get more accuracy. And the rest of the bone was meshed with a more coarse mesh because there we needed less accuracy. And there was less interesting things happening. So you can vary the mesh size to kind of optimize your size of your model so that it's still computationally efficient. Now the computational load, if you think about the excavator and you build a model, it has like 10 to 50 bodies, maybe 10 to 100 joints, depending of course on the level of details. When it comes to human, you start with 16 bodies, but it can be 270 or more, and joints 16 or more. Then if you add 12,000 degrees of freedom from the final element of a single bone, so here you get a cup of coffee and you get the result. Here you basically are waiting and waiting and waiting before you get the result if you try to do it all in one simulation without any optimization. So what you can do, you can go for model reduction. So you start with a volume. You add mesh and material properties to it. Then you add some massless beams so that it's connected to the centers of locations of the joints. And then you perform a model analysis. And what model analysis gives you is deformation modes. And those deformation modes basically present different ways how the bone can deform. Yes, so it can compress, it can bend, twist, all the possible modes, depending on the loading, on unit loading in a small scale. And then it's superimposing those different modes. So you can select, let's say, 10 different modes, which are the most important. You can actually see what happens on the individual parts without simulating 10,000 degrees of freedom, but you have maybe 20 degrees of freedom, or 30 or 50. So you get closer to a model which you can deal with in the multibody simulation. So for the simulation, what we need the environment, we need natural movement, we need verification way for the model, and then we have some models, and only then we have the simulation. Now what comes as an environment? You can see. So for example, exercising equipment and human subject, that's our environment. Then motion capture allows us to get natural movement. Of course, we can get it in a couple of different ways, but motion capture is the most popular. Then for verification, we need to have some external measurements that we can compare it to. It can be either the motion that we use as a verification data, but it can be force sensors or additional sensors, for example, accelerometers on the body or something. So you just measure a couple of quantities and then you compare if you can simulate the same sensor in the model. And if you get the same results there, then you know that your model is performing well. But if you get something completely different, then you know that your model parameters are off. And you have to find out what to apply to make it better. Then models of individual elements, so these are bones, joints, muscles, and contacts. And then finally you get the simulation. So again, some more detail about the simulation. So when we have a human model and a motion capture, what we can perform is inverse dynamics. So we can basically drive the model and see what our kind of forces would be there. If we add flexible bones, well, in inverse dynamic, flexible bones wouldn't work because there's some inaccuracy in the model motion description. And if the two markers move with respect to each other, you would see that the bone is compressing with some kind of extreme force, which is not realistic. So because of the errors in motion capture, you cannot just apply them in inverse dynamic, the flexible bones, and assume that the motion will drive them, because it will create some forces which are not there, really. It's not like you're pulling the model through the markers, including all the inaccuracies. But in a forward dynamics, you can do tricks. So if you compare if you combine the results from inverse dynamics and flexible bodies, you can build the forward dynamics model. So you know how the model should move, and now you have to design a controller for the muscle that will cause this motion to happen. So as an input, you use the inverse dynamic results, which tell you how much each joint is moving in every time frame, and then you make a controller that tries to pull the muscles in such a way that you will follow that. And if it happens correctly, then your model is actually driven like a real human, and what you get a ground reaction, you have bone strains, you have muscle activities, and joint loads. So you have a bunch of parameters that come out from the simulation. Now these are some examples from the studies, and I don't know if they run straight away or do I have to click them. see. Okay, so this one guy is exercising. This is just an example for seeing that you can keep the model stationary using just contact. So how he's held on that place is basically we have some kind of muscles and body parts modeled, and they keep him in place using just the contact modeling, so he's not sliding there, he's not fixed to the model, but he's using contacts to keep him steady. How he's being moved is basically before there was a, we didn't have any motion data for that guy. Basically what was there, it was just a bar pulling him by the chest and moving according to the prescribed trajectory, and that was kind of used in the inverse dynamic. Then the muscles learned that, okay, we want that motion, and that motion was replicated in the model. Then this one, this one. Oh, I can play them separately. So let's go here. Okay, this is the one that is here. So I don't have a working model of that slide in this computer. But anyway, there's a motion for all of those, and I'll try to provide it to you as a supplementary material to this lecture recording. And the next slide. This is walking, and again, there should be a video. Maybe I have it in a different folder. Let me see. So this is, for example, leg press. So you can see the flexible bone being deformed, and it changes color while the loading is increasing. You can see the arrows which show the forces between the foot and the pressing pad. You see the weights moving, but that's just the animation. The actual force is applied actually to this arm that is being pressed by the guy. And here, basically, lower body model would be sufficient. We use full body model, but not full body muscles. This is the leg extension. So here the torque is actually applied to simulate the loading. And here the leg is also using contact to touch the surface of the support. So the leg can move with respect to the support. The pelvis is fixed, so the upper body is totally not moving. We don't use any muscles there. Here the muscles on the lower body are not visualized for clarity, but they are there to actually cause the motion and simulate the movement. This is squatting, so that's another modeling. So here the legs were firmly on the floor, so you can attach them with bushings to allow some motion but not to fix them, and that's the way how you can model the support. You can see that the fingers are not clenched on the bar because it's not needed. They have to actually hold it, so you can actually rigidly attach the bar or using some kind of a bushing, and that gives you a decent result to simulate the whole motion. I think that this is one. So this is one example when things goes wrong. So if you try to simulate a deep squat and the muscles are not really there, so now at this point, basically the muscle jumps to the other side of the joint. So the muscles which should extend the body to move forward actually are pulling it down. And basically the guy loses stability and behaves completely off from what should happen. So that you have to be aware that when you try to do the biomechanical simulation, this is something that you will see more often than the successful model, so before you get it. Here is walking, but it doesn't work. This PC. Maybe it's this walking that works. Yeah, that's the same walking, but just working. So here you see the walking, and there are contact elements on the feet, which make look like a bare feet, but still this provides the contact for different places. The foot is rigid, which makes a little bit complication when the forward swing starts, because usually you bend your toes to actually have the foot as close to the ground as possible. Not many people are marching while walking, so when you try to replicate it, it's quite tricky. And of course, you have to keep the stability of the body while he's walking. And that's not easy when you have just two legs. And if we walk with the femur model, so that's the flexible femur model here from the front, so you can see the stresses appearing in different locations of the bone whenever there's an impact. Then they are kind of higher, so they are more visible. Okay, so these are the videos. Then going forward. This is the squatting. Then there is bicycling. So bicycling, it's just modeled the pelvis attached in a floating joint to a seat. And then there are crank. Actually, you don't need the crank with full thing. You just need the individual pedals moving with the torque applied. For visualization, we actually modeled the whole thing. And one interesting thing from that was we actually measured the forces on the pedals. And what came up is that the guy had almost twice as much force in one leg than the other. He was a soccer player before, and that caused him to kind of strengthen his half of the body more than the other, so he was more trained on one side. So there is a dominant side, and normally you wouldn't see it from the side when you look just on the motion study. You need to go back to the forces. This is jumping, just the hopping in place. Of course, this is quite difficult to make the model stable in the flying phase and then landing. So there is a need for some kind of support or external forces which are added to stabilize the model. But generally, it's possible to simulate the jumping. In here, we didn't simulate the hand motion, so that it's unnatural, and that has a big effect also on the flying phase. So when you're loading, you're balancing your body with the movement of the whole body to actually structure. And in that case, basically for loading, you need to know the mass distribution quite well, so that the replication of motion would still give you the good result. Then on the side, there is just walking, but that's, I think, not that interesting. And some results from walking. So from the side, you can see the phases of walking. That's probably something that people don't think about when they are just moving around. That we have something like a heel strike, when we strike the ground with the heel. We have a swing phase when the leg is moving forward. And then we have also the double support phase when both legs are on the ground. And what happens in the tibia, for example, during that, if you see the strains around the cross-section of the bone, you can see that strains on one side are positive, on the other one are negative. So in the part where the leg is touching the ground, there's also a lot of strains on both sides. So it means that tibia is being bent. So your leg is bending while you're standing. And then when you're moving forward, this bending goes down because it's only the muscle pulling the leg, so there's some bending relation to the inertia. And then again, when the heel strike happens, you get another disbending. So that's how most of the load are taken. And of course, if you look at the absolute value and sum them up, you see that it's more negative than positive. So you see that in addition to bending, there's compression, which is also logical. The compression corresponds to your weight somehow, or multiplication factor of your weight. Then if you do the knee flexion, depending how you do it, whether you do it slowly, medium speed, or fastly, you see how the force is actually developing. And it's a thing that when you do it quickly, you optimize. Yes?
Actually, ideally, both legs they have the same strength, ideally, in a human body.
Yes. Normally they have the same strength, but usually you are doing something and you have some dominant side. So if you're, let's say, right-handed, your right hand will be probably stronger if you try to, for example, play different games and try like pulling a rope or something, what you can do with the right hand.
Yes.
And the same is with your legs. If you do a sport which is asymmetrically loading your body, like if you play soccer, you're scoring goals with shooting the ball, and you do it with your dominant leg. So of course you will have stronger muscles on that leg. And that's the asymmetry. If you're a tennis player, your one hand will be far stronger than the other because you're bouncing with one hand and the other hand is just for, let's say, keeping the balance. So those odd loads usually cause the imbalance and your body is not symmetrically. So we are in general quite symmetric, but as we train or do different activities, even though we don't realize that, let's say carrying a shopping basket or let's say shopping things, you carry it in the hand that is kind of stronger. and you make that hand even stronger.
Yeah.
So then it's lighter, and you always go to that side, and you switch less. So that's how the asymmetry is accumulating. But what happens if you try to do the exercises quickly is that you have very smooth curves of the force distribution. Because you apply the impulse load, you kind of go until the limit, and then it kind of naturally stops. That's how you try to feel the force. And then it goes down, and then just before hitting the bottom, you don't want that hit because it's unpleasant, you apply an impulse force to slow it down. That's what happens when you do it quickly. Now when you try to do it slowly, you have lots of spikes there, because what your muscle controller does, it's not very quick. So you're just applying some force, you feel that it's too fast, so you're backing off. Then you feel that it's not fast enough, so you're applying a force, and that's the jaggy way of doing it. So you can see that then the starting point is delayed, because you kind of first sense, am I moving or not, and then you're actually applying force. With making it fast, you just have an impulse that you start, you put an impulse of force, just push it, and go back. Now, if you have the knee extension, so it's the other way around, the force application is slightly different places. Here you see that medium and fast is almost the same, because the speed difference was not that different for that guy. And here, again, when you do it slowly, you have higher impulses of forces, because whenever you're kind of close to a turning point, you try to kind of stop the motion or accelerate without hitting the stop limits. So that's what causes the jagginess, and your control system is generally slow. And when you try to do it fast, again, you have a peak force, you just go with the flow, then allow it to go to the limit, and then slow down. So you just apply short impulses, but like targeted impulses of forces. If you try to do something slowly, you're trying to distribute the force over time, and that usually produces some kind of movement. Some differences about the knee flexion and extension from the subjects that we have. So people said that the flexion was more difficult to perform, especially when you try to do it slowly, and the highest low on the tibia strains. In the knee extension, the tibia can be easily overloaded with the forces if you just go too far. And low speed results in a peak knee force at the turning point. So these are like more results from that kind of study. Then the other example, as a short example for the end, for the biomechanical studies, the biomechanical study on a lizard. So this is a savanna monitor, which is a lizard which is more or less the size of a big cat. It has a long tail. Basically, the tail is the second length of the rest of the body. There are some dimensions. So tail is 440 millimeters, and body length is 290. So actually, tail is longer than the rest of the animal. They live around 10 to 15 years in captivity. Live, they probably live shorter. They eat some small animals, insects. That's what they do. And here is the lizard prepared for the motion capture experiment. So there is no protocol for the animal. So you have to decide where you put the markers. And one thing that you realize is that putting markers on a lizard is not that easy, because the body, even though it's relatively large lizard, you still have the markers being very close to each other. So when you look at different angles, you can easily find the angle where the markers kind of align in one line and you don't see them. So that's one of the difficulty here. Of course, you start with the animal measurement. So you have to have some tape, measure the joint points. So we could not take the CT scan for the animal because it was not justified by medical reasons to put any radiation to the animal or put it to sleep to just scan it. So we had to live with just a measurement from the outside. But of course, if you measure joint to joint, you get a decent representation of what is inside to make a skeletal model, at least for kinematic analysis. And these are the measurements which are taken. Then this is how in practice looks taking motion capture. In the middle there are force plates, and the idea was that the lizard walks through the force plates so we can measure the ground reaction force. The things that could go wrong is that the animal could basically go anywhere except the place where we wanted to go. Convincing it to go straight was quite a difficult thing, and basically calling it helped a little bit, but it preferred to walk on wooden floor than the metal force plates because they were cold, even though that this was like plus 40 or so because it was in Barcelona. Finally, it walked over the force plates, but with more than one leg on the force plate at a time, which means that you don't see really well the distribution of the force between the legs. So you can do something to estimate, but it's not that easy. The other difficulty is that lizards can utilize either high or low level walking, because the paws goes like hands and arms grow from the side of the body, not in the front. Like if you have a horse, the horse has the joints on the bottom, not on the side. And because the lizards have them on the side, they can actually do something like this, and they lie on their belly quite easily. So when they are walking, they are dragging their belly on the floor quite often. That's called the low walking. So you have to take you have to have quite a lot of patience to wait for them to do what you want them to do. And of course, you can capture something. Then the other interesting thing is how they move their legs. So basically, they move the hand like this, and then like this, and then they drag it on the upper side. So whatever marker you put on this side will be demolished after the first step. So you can only put markers on the side of the paws. So you cannot monitor additional rotation. So that limits quite a lot how you can measure it. So the only way to get it right probably is to have capture and have some kind of visual stickers or something that is flat that the animal won't take off, so that you could track it during the motion. So we had 2 measurement sessions, 12 captures per session, so like 25 markers were used on the body, as you can see. We used a gentle double sticky tape to attach them to the body, so that it was easy to remove like a plaster. Marker size was kind of large that we had available. We would need probably like 3mm marker size and higher resolution cameras to get it right with more accurate body motion. The walking style is kind of difficult, so it's difficult to attach the markers to the feet, and either the markers are hidden under the belly or they are removed while walking. So this is something to always think about when you think about animal studies. Think twice. It's really difficult to execute them to get results. Probably if you try it with an elephant, you would have a lot of space to attach markers, but of course then if the elephant is crazy, you have a lot of problem. Crocodile also would be better from the size perspective, but again, behavior of a crocodile is highly unpredictable, and you would need to have some real experts to know how to make them move how you want them. But still interesting study to see what you can do with the simulation. Okay, I didn't have the motion capture here from the study, but still, that's what I would like to tell you about the biomechanics today. And I'm slightly over the limit, so thank you very much for your attention, and hopefully you get some interest in the topic and you do something interesting from the research perspective in the biomechanical field. And on the final exam, I'll try to prepare some questions regarding to that topic. So try to have a look at the lecture slide at least at some point before the exam, and think about it so that you're ready for the questions. So thank you very much, everyone, and see you on another lecture maybe.